Well, good afternoon. This is 12:36. I'm about 6 minutes late getting started, but one of the reasons is Clark needed another book, and I had to go to my office to get one, and he hasn't made it back from his car yet where he carried his old book. So anyway, let's go on and get started with today's class. This is Math 227, Cal 3, and right now I'm the only one in the room, but I'm expecting Clark back pretty soon. So we'll start from this slide, but we will, before we get to that, let me go over a few announcements. Now, some of these will pertain to some more than others, but let me just hit them all. The first one, I'm thinking only one of you would be in the least bit interested in this information, but maybe some of the others of you know someone who would be. It's a flyer that came in this weekend sometime. Are you the next Miss Lawson State Community College? For those people who are thinking of participating in the Miss Lawson, I want to say it's a contest because that's really what it turns out being. Student body folks vote on it. But if you're interested in participating on it, there are two informational sessions coming up. Now, one of them is right now, okay, is today. Not right now, but it'll be later today, from 2 to 4, and this is over in the Space Center on the Birmingham East Campus, just barely on the East Campus, because it's in that new Academic Success Center, which is right on Wilson Road, okay? Wilson Road is what divides East Campus from West Campus, but it's on the east side, I'm sorry, on the west side, I've been saying east, the west side of the of Wilson Road. So it is there at the that new building. And the Space Center, I can't even tell you which floor it's on, but you go in and I'm sure you can find that out. But it's this afternoon from 2 to 4. The information is that's called an interest forum for the Miss Lawson State pageant and activities and that type of thing. Oh, here it is. It's in room 220 of the Academic Success Center. That's where the Space Center is. I went on and made this announcement, so I'll make it again for you because you may be interested. Are you the next Miss Lawson State?
I don't know.
There is an interest forum today from 2 to 4 at the Space Center, which is that new building over on the Birmingham West Campus. And it's in the Space Center that's in that building now. That's up in room 220, Birmingham West Campus, just across Wilson Road from the East Campus. But there's also a session tomorrow, if you can't make today's, because you're going to be in calculus class, and that's 11:30 to 1 o'clock, and that's in this building, the A building, room 182, which I'm pretty sure is the testing center down, near the front desk, and that's on the Bessemer campus tomorrow from 11:30 to 1. Now, we only need an hour and a half of interest forum. They have a 2-hour interest forum, so I guess we process our interest more quickly. Now, here are the requirements for Miss Lawson State. Currently enrolled at Lawson State Community College. Okay? 3.0 cumulative grade point average or higher. Completed and or currently enrolled in a minimum of 16 credit hours at the 100 level or higher. Active in an extracurricular activity or organization. And if you want more information, you can contact Ms. Leslie Harper or Ms. Janine Jones. They're both over on the Birmingham West Campus. I bet you they're both in that new Academic Success Center. But here on this campus, Ms. Kimberly Moore, her office is right across from the testing room down there. So, now, another thing that's happening today, in fact, it's already happened, but just in case you're interested, today, this morning, there was an official signing ceremony for the Alabama State University transfer memorandum of understanding. Now, I don't know what all that means, but it sounds like to me they've just made it easier to transfer from Lawson to Alabama State. Can't see how it could have gotten much easier, but evidently there's done some things that makes it really easy to do. So if you are interested in going to Alabama State or know of someone who is, this is a pretty good deal for y'all. Okay? And that was at the Academic Success Center this morning at 11. Now, also, sometime Friday or over the weekend, sometime, they finally published the final exam schedule for this term. Doesn't really matter much for this class because it's going to be a take-home final, and you just got to get it back into me. But the strange thing about it, I noticed they did it last term too, but I thought maybe it was just because it was the first term we had done it. You know, last fall was our first term we went to 8:30 classes rather than 8 o'clock classes, and that changed everything that got moved back 30 minutes. Well, they still started the finals at 8 o'clock, okay? Well, in final exams week. So for people who were used to being here at 8:30 for our class, those classes, and all 8:30 classes, their finals start at 8 now. If you're, that's Monday, Wednesday, or Tuesday, Thursday. Okay, so that's coming up the week of the 29th of, wait a minute. This is not what was on the college calendar. Unless they've changed something here, I'm going to have to send an email. I'm going to get out of this just momentarily and pull up the college calendar. They've got this wrong if I'm reading it correctly. And I think I am. I didn't even notice this until just now. I even announced it this morning. And for some reason, I'm not getting this to open. Okay. Sorry about this. This is an unexpected delay, but I want to give you good information. And I'm going to turn on the projector, even though it's not math yet. But
do you think that the moving to 8:30 helps anybody to get here on time more?
I think they just sleep a little later. Actually, I'll take that back. For people with kids that they had to get to school and it was difficult for them to do it before, maybe a little bit better. The rest of the people just slept 30 minutes more. Yeah, I don't think it made any difference in the world. But there would be some who had kids that, yeah. And it took some pressure off of them. If they had to drop the kids off, they don't worry about them being there outside of a school building waiting for the doors to open or something like that. So I think that part was okay. But the rest of it, no, I haven't noticed that my 8:30 classes, that they get there any sooner than they did 8 o'clock classes before. Okay, academic calendar. Okay, April. Yep, you see it right there. Final exams start on the 30th, not on the 29th. And if you go to May, we'll see, maybe they got that wrong. Yep. And that's the last day of final exam for the regular term. So this thing is wrong, or the calendar is wrong. I have a feeling this thing is wrong because the calendar, I think, had to be approved by the state. So I've got to send an email. I didn't even notice that this morning. Okay. But here was the issue that came with this. Oh, boy, they've got it totally wrong. If you're graduating, are you graduating this term? Okay, good. If you're graduating, then your grades are due in by Friday, May 4th. If you were not graduating, then they say here they're due by noon on Monday, May 8th, which is hard to do if that's the last day of finals. So there are several things wrong with this. I've got to make those, get in touch with somebody about that, because it's totally wrong. So sorry about that. All right, let's get out of here and get back to math. This has been a hard class to get started. Okay, did you see the book?
Yes, sir.
Okay, and I opened to the same pages here, and the pages are identical except for the page number. It's 12.2. In mine, it's 828, and I think in yours it's 824, isn't it?
Yes, sir.
Yeah, but the pages look identical. Now, I'm not saying every pair of pages will, but these look identical. And,
Even the examples.
huh?
Even the examples.
I think so. You'll see in just a second. That's where we're going to start at example 1. Okay, so we'll start from current slide. I think everything's going here. Isn't this your example 1? For the vector value function r of t equal to ti plus t squared plus 2j, find r prime, then sketch the plane curve represented by r of t and the graphs of r of 1 and r prime of 1. Is that your example 1? Top of page.
I'm looking at the wrong one. Yes, sir. That's it.
Okay. Top of page 25, right?
Right.
Okay. Now, I'm going, if I ever call numbers, I'm going to call this one. I'm not going to remember what to subtract 4 from yours is to get yours. But the otherwise, it looks just like it. All right. So the first thing we got to do is take a derivative, right? We are given r, and I need to get my pen color set up. There it is. So we're looking for r prime. And since I can't write in bold, I do the little arrow. So, excuse me. Sorry. All right, you awake? Okay. How do we do r prime? How do we do r prime?
So, I was not here last week.
Oh, that's right. Well, it's component by component. Take the derivative of the first component. It's derivative of t. And by the way, it's dr with respect to t. Okay, so what is the derivative of t?
T to the second power over 2.
No, that you're integrating. I'm differentiating. Okay, exponent 1 times coefficient 1. Drop the exponent by 1. It's t to the 0, which is 1. So that'll just be I. Okay. Now the second thing I do, if I know it's a unit vector, I put a cap over it rather than an arrow. And that way I identify it for myself and hopefully for you too, being a unit vector. The book just bolds all vectors. I like to identify unit vectors if I know them. Plus, okay, can you do the derivative for the second component? You don't really need the chain rule, but it's just the power rule.
That's what I said.
Yeah.
So you have T
Yeah.
plus, let me just be T, and then it'll be times T squared plus 2 to the 0.
Second?
So it'd be T times 1.
It's, yeah, T. Wait. Okay, sorry. Exponent 2 times coefficient 1. 2 times 1 is 2. Drop the exponent by 1. T. Derivative of 2 is 0. plus 2tj. Okay? Now, we've done the first part. We found r prime. It says, then sketch the plane curve represented by r of t. Okay? All right. Sorry. So let's do the plane, our coordinate plane here. And we'll tick off a few points. Okay, I don't know if that's going to work or not, but let's do it. All right. They don't give us any limits on t, okay? I thought they would, but they don't. And no, I haven't chosen well, have I? Let me choose better. Woo! Okay. Okay. I just happened to glance at the book and saw they graphed it too. Oh. All right. I'm going to put my x-axis way down there because, and let me tick off a few points here. Okay. Now, when t is equal to 0, what do we have? Look at r of t up here. When t is equal to 0, where are we? Okay. 2j. Yeah, exactly. So that's 2 on the y-axis, 0 on the x-axis, 2 on the y. Because the i's represent the x's, the j's represents the y. So 2j, so that's where we are. Okay? Let's do t equal 1. What would that give us? X-axis would be 1, y-axis would be
1 plus 3j.
Second?
1 1i plus 3j.
Okay. Where'd you get a 1/2? Doing this one up here. So when t is equal to 1, that would be I. So it's 1 on I. And then 1 squared is 1 plus 2 is 3j.
That's what I was saying.
Oh, I see. I'm sorry. I thought you were saying 1/2. Okay. 1, 3. Okay. Let's jump over to minus 1. Minus 1 would put you back here. X would be a minus 1, but the y value would still be 3, right? Because minus 1 squared is, okay. So that would be there. Then when you go to x or t equal 2, that would be 2 on the I, on the x-axis, and
Plus
6j, right. That's 3, 4, 5, 6, j. And the same thing on the negative side, only it would be a negative. There, I can't draw dots very well. And then for a 3, it would be 3i plus 11j. Let's see if we can get up to 11. It's 6, 7, 8, 9, 10, 11. Just barely do it, okay? There, and then same thing here. So this would be a good old parabola, okay? There is the graph of r of t. The plane curve represented by that. Now the only thing you have to add to it is put an arrow, meaning this is the direction of increasing t. It starts negative infinity here, it goes down and back up again. You only need to put 1. I put 1 on each side. Yeah, you only need 1. Okay. They put 1 on each side too. Good for them. All right. Then it says, then sketch, okay, the plane curve represented by r of t. We did it. And the graphs of r of 1. Well, let's do r of 1. R of 1 would be what? I plus, we already did it, what would that be? 3j, perfect, okay? So that's that point right there, okay? Now actually the vector r is this vector right here, Okay, this is r of 1. Okay, it's a vector going from the origin to that point. Now, and they did that in the book too, yeah. Okay, now, the next it says, sketch the graph of r prime of 1. Well, here's r prime, so let's do our r prime of 1. And remember, when you take a derivative, the derivative is also a vector, and that would be what? I plus 2j. Perfect. Okay. Now, to graph that, we start with this point here because that's where it's located, and we go 1i to the right and 2 i's up. Okay. The i's have it, if I can find it. There it is, somewhere about there. So this would be like this, and this would be 1 i back and 2 i's down. So somewhere like that. So this would be the curve. It shouldn't be a curve, it should be a line there. And this is r prime of 1. It's tangent to the curve at that point. Okay? And if you plug that in, and it, as I said, is also a vector, and this is its vector representation. And you could have drawn that vector anywhere here, but it needs to go right there, touching the point, because it needs to intersect at 1, 2, because that's where R intersects. No, I'm sorry, 1, 3. 1, 3. Does that make sense? Okay. So let's see how they did it. Okay. Differentiate on component by component basis to obtain r prime is equal to I plus 2tj, just like we got. From the position vector r of t, you can then write the parametric equations t, x equal t, and y is equal to t squared plus 2. Basically, this is your x. A scalar function x, there's your scalar function y. xi plus yj. So that's where they got those. Okay. And the corresponding rectangular equation would then be, because x is equal to t, right up there, you can put this t, instead of t, put x, so that would be y is equal to x squared plus 2. And that, sure enough, is a parabola. Okay? Vertex at 2, 0, 0, 0, 2. Vertex at 0, 2. And axis of symmetry is the y-axis. Okay? So when t is equal to 1, r of t would be, going back to your r of t up there, it would be I plus 3j, just like we had, and r prime would be, when t is equal to 1, would be I plus 2j. And there it is. And then here is the picture. R, okay, the curve represented by the values, the endpoints, the terminal points of r of t is equal to this thing here. This would be where they would be. When x is -3, you'd be up there. When it's -2, you'd be here. When -1, you'd be there. 0, you'd be there. 1 would be there. 2 would be there, and on and on and on. Okay? Now, the arrows go indicating which direction t's are increasing. Well, they may have gone the other way. You can't ever tell sometimes. Okay? And the r vector, though, at r of 1 vector, these are the endpoints at all your various t values. But r of 1 is this vector right here. If you did all these other vectors, they'd all be going to points on the curve there, and it would be a big mess, but we just do the endpoints for those. This is your R of 1 down here. Your R prime of 1 is from this point here where it's touching 1, 3. Then you go right 1 up 2. Oh, it was, I plus 2Tj. Yeah, plus 2Tj. And so that would be this vector here. And in reality, they draw it with it starting there, but a vector is infinite, technically, so it would extend back this way as well. Okay. All right. I had all that coughing and sneezing that I did. Has me all stuffed up now. Okay. So, any questions on example 1? And that goes right by your book, right? Yeah. All right. Now, they're skipping example 2, so let's back up and do example 2. For the vector value function, R of t is equal to cosine ti plus sine tj plus 2tk, okay? Find each of the following. A is R prime of t. So what is R prime of t? Now, 3 dimension, you just do it 3 times rather than just 2. Drawing the thing will be a pain in the neck if they ask us to draw it, which I'm afraid they will, but let's go on. What would be R prime of t? Negative sine ti plus cosine tj plus 2k. Okay, 2k. All right. Got it. That's the A part. The B part says do R double prime of t. R double prime of t. And what would that be?
Negative cosine.
You got it. Ti minus sine tj
and plus k.
0. Because the derivative of a constant is 0. So there is no k component. 0k. So that means your second derivative is always in an xy plane. Now it doesn't have to be the xy plane, but it's some plane parallel to the xy plane. Okay, so that's the B part. The, huh?
Why is that? Why does it always have to be two-dimensional?
What's that again?
Why does your second derivative always have to be?
Well, it doesn't. This problem it does because the second derivative is the k component is 0. It's not always, no. Okay, but in this problem it is. Okay.
That's what was confusing.
Yeah. All right. Now the C part. C part calls us doing something else that we have already done. And I'm going to start it over here because it's going to take a little more room. R prime of t dotted with, that's a dot product, remember, with R double prime of t. Now, do you remember what a dot product does?
Use a refresher.
Is what?
Use a refresher.
Oh, okay. What it does is, if you're dotting these two, and these are those two, you multiply, okay, number 1, there results of a dot product of two vectors is a scalar. It's not a vector anymore. So this is not going to have any components in it. And here's what you do. You multiply the first component by first component and add to that the second component times second component, and add to that the third component times third component. So what's the product of your first two?
Side there.
It's what?
Just trying to think about the side there.
What about the sign there?
That would be a sine, cosine.
Sine t, cosine t. Perfect. Then the product of the next two will be, and you add these together.
That would be so the plus, a minus,
Minus.
Cosine t, sine t.
Perfect. And then the last is going to be
Plus 0.
plus 0. You got it. And what does that give you? And notice there's no components to it. These are just values, functional values. And what's sine t cosine t minus sine t cosine t? 0. Now, that tells you something about this set, but I'm trying to think if it will be for every set. I think so. That your first derivative dotted with your second derivative is all, at least this one is going to be 0. And what does that mean? These two vectors are perpendicular to each other. Somewhere in space, they're perpendicular. And these both happen to know. This one's in 3 space because it has a k component. This one's in 2 space, but they still are perpendicular to each other. Okay? That's what that means. All right? Now we'll do the cross product. R prime of t cross R double prime of t. Okay, now, let me tell you something about, do you remember much about cross product, or need a refresher there too? Okay. Cross product is a vector product, okay? Your answer is going to be a vector. And it's going to be a vector that is mutually perpendicular to both of these. So wherever these two vectors are, this one's going to be perpendicular to both of them, okay? So what we're going to do here, and these are technically 3-component vectors. It's just this one's a 0. So here is, to me, the easy way to cross product two vectors. Okay, do you know what a determinant is? Okay, I'll show you, and it may come back to you or it may be brand new, but this is a pretty simple application of it. The first row in this determinant are going to be your components of this vector that's going to be the product here. Okay, so that's just going to be I, J, and K. Okay, the next row are your whichever one's listed first, the R prime, and that will be minus sine t positive cosine t and 2. Okay, your third row is going to be the components of the second vector listed here, which is R double prime, which is minus cosine t minus sine t and 0. Okay. Now, there's 2 ways to do a cross product. Okay. Here, to me, is the easy way. Okay. Repeat the first 2 columns. I and J minus sine t and cosine t and minus cosine t and minus sine t. All right. Now, I put these two vertical bars out here, and that's not quite accurate, because those are indication that we're taking the determinant of this. But we're not really, because you can't take the determinant of anything but square matrices. So technically, we're taking the determinant of this matrix here, the 3 by 3, before you added these two columns again. But to make things easy, to keep up with the sign changes, this is the easy way to go. Okay? And what you do is go down a diagonal. Okay. Now, I sort of got off there. Let me do that a little bit neater. Okay? A little bit.
We did do this for an example.
Okay, I thought we had, but I couldn't remember if you were here for it. So we go down this diagonal here. Okay? And this is going to be an I component. But what's cosine t times 0? 0. So that doesn't give us anything. Go down the next. Now these are your main diagonals, the downhill diagonals. And these are always multiplied in the positive sense. So j times 2 times negative cosine t, that would be minus 2 cosine t j. Okay? Then we go down the next downhill diagonal, and this is a minus sine squared t k. Okay? Now, what we do is go up the other diagonals.
Would it be a positive sign?
Well, because you have a minus here and a... Okay. Yeah, it's the positive of this, but this is a plus minus. Oh, you're right. I couldn't see my minus. You're right. That is a plus. Sorry, my writing stinks. Okay. Okay. Your writing must be much better. Okay. Then you go up your diagonal there, and when you go up a diagonal, it's the negative of the product. Okay? Well, this is a minus times a plus, which is a minus, but you're going up a diagonal, so that makes another minus. That makes a plus cosine squared k. Okay? I wish I'd have written it underneath, but I forgot to. This will now be, it would have been just a minus 2 sine t, but since you're going up the diagonal, that's a negative of that. So that's a plus 2 sine ti. And then this last one is a 0j. All right? Got it so far?
Yes, sir.
All right. So this gives you a 2 sine ti, if I could write, minus 2 cosine t j plus, and what do you notice you have there? 2 k components. You only have one each of I and j because one each of those is 0. But here you have
Plus
sine squared t plus cosine squared. Oh, I thought my t, didn't I? Okay, and what is sine squared plus cosine squared?
1.
1. So that's just plus k. So there is the result of the cross product of these two vectors. 2 sine ti minus 2 cosine tj plus k. Now, that's all they're looking for, so I'm not going to jump into it any deeper than that. I sort of want to, but I'm not.
What else could we do?
Well, I was just going to say, you could go back and confirm for yourself that r prime was perpendicular to this, and you do that by doing a dot product, because if the dot product is 0, they're perpendicular, right? And you'll see this is minus 2 sine squared t. Remember, dot products, you don't carry your components anymore. Minus 2 cosine squared t, and then the dot product of this and that is 2 plus 2. Well, this is minus sine squared plus minus 2 sine squared t minus 2 cosine squared t. No. Minus this times this is a minus sine squared t, because of that minus 2 cosine squared t. Well, minus 2 sine squared t plus minus 2 cosine squared t would be 2 times sine squared t, or minus 2 times sine squared t plus cosine squared t, which is 1. It would be a minus 2 plus 2 equals 0. So sure enough, those are perpendicular. And then you could do these two the same way. Minus 2 sine t cosine t minus 2, no, plus 2 sine t sine 2 sine t cosine t. Those add to 0, plus 0, sure enough, is 0. Okay. So yeah, those are both perpendicular. This one's perpendicular to both of those. Okay. That was the only thing to do. Okay. And we got the same answer they did. 2 sine t I plus minus 2 cosine t j plus k. All right. So we doubled the class size. Next came in. All right. Yeah.
Are we out of school Wednesday?
Okay, yeah, I should have said that earlier. Let me say it now since we got twice as many people here. Yeah, you weren't here last week. Okay. Our beloved chancellor of the two-year college system deemed that it was necessary for all instructional, full-time instructors in the whole two-year college system in the state of Alabama to converge on Montgomery Wednesday, a class day. It makes no sense. We have professional duty days at the beginning of a term before y'all ever start school. We have a whole bunch of professional duty days at the end of the term after y'all are long gone. Why couldn't it have been one of those at the beginning or one of those at the end? No reason at all, except he's just wanting to show he controls everything. So he just has ruined a whole day of class for all full-time instructors. Now, if you have an adjunct instructor, then your class still meets. So no, the college is not closed, but only staff and part-time instructors will be here on Wednesday. So what I'm going to do at the end of the class today is see where we leave off here, and I'll take you to Blackboard and show you the next 1 or 2 Blackboard sessions because we probably didn't start and end at the same time last time I taught the course. So, and if you go over those on Wednesday, then when I come next Monday, we'll start where that one left off. Okay? Where those left off. So yeah, no, the college isn't closed Wednesday, but if you only have full-time instructors as instructors, then you probably don't have a class. Now, I heard some of the, and the only ones I heard doing this was a new instructor, full-time instructor on the Birmingham campus. The way the thing was worded, she thought the classes still had to meet, so she had to line up someone to teach her class, or to sit with her class anyway. So she's requiring her students to come into class on Wednesday. But their work study student, someone like that, is going to call a roll and give them assignments, and they're going to work at it in the library or something like that. It's just utterly ridiculous, okay? I'm going to just assign you ones on videos, and you just knock yourself out with those.
Well, my first teacher said that a class was canceled, but I said if Dr. Fowler cancels class, it's serious. There's got to be something.
Well, it is. They're requiring us to be there, and it's the biggest boondoggle we've had in years. But it's a fairly new chancellor, and he's just trying to show his money. I think so. That's the only thing I can figure, because there's no excuse for it. We have plenty of other opportunities we could have done this. Now, this example 2 isn't done in the slide set, but you see it is done in the D is done at the bottom of the page, and they did it slightly, well, they did it very differently than me. But basically it turns out the same thing. What they do, and I'll show you the other way to do this. Now, I'm going to take off my construction lines here, but I want you to remember basically what they look like. Okay? In fact, I'm going to leave them on, I think. Okay. The I ones, notice here, it's going to be the product of these two, right, minus the product of these two, right? Well, that's exactly what we did. The product of the down one is a positive, and the up one's a negative, so that gave you your 2, and the down one's a 0, so it just gave you 2 sine t I. Then the J one is going to be, the positive is down like this, that's a minus 2 cosine t, and then the up one for J is going to be, again, 0, and that's where you got your minus 2 cosine t J, okay? And then your K one is going to be, oh, and by the way, I just did for J these two, but you see this one was originally over there. So that's going to be this cross product here. But it's going to be the negative of it because that moved in front, okay? So hang on to that thought. This came from here, but it's the negative of that because if you had it over here, it would be like this, okay? And then the K is going to be just here, which is exactly the same as these four here. Cross down this way, that's the positive, and cross up that way for the negative. That's exactly what we have there. So now I'll erase them and show you that's indeed what we've got. Okay? So let's get all these out of the way. Whoops, I just lost the C in cosine. Okay, they're always trying to leave the room. Okay, there we go. Now, if you just ignore these two, you know, just end at the 3 by 3, okay, then it would be I times this cross product here, which is exactly what we had. But then it's minus J times the cross product. What you do is you wipe out the row and column and what's left. So this times this minus that times that. But it's a minus J, so it flips the signs around. And that's what you had there. And then it's plus K times this cross product there. And again, the down diagonals are positive and up diagonals. And it's just, rather than doing 3 steps, you just do 3 down and 3 up, and you got it. Rather than doing 3 different matrices. Okay. But it gives you the same result. Okay. That only works for 3 by 3. Don't try it with a 4 by 4. It won't work. Okay. All right. Now, I think we're now ready for the next slide, if I can find it here. Okay. We did that one. Here, this is top of page 830 if you got this book, 826 or whatever on your book. The parameterization of the curve represented by the vector value function R of t is equal to f of I, f of t I plus g of t j plus h of t k. Now just, I know Vince was probably here before reminding you, this is a vector function. These functions here are scalar functions, but they're components of the vector for this vector function. So just keep that in mind. The f, g, and h are scalar functions. The r is a vector function, which means it has components, and those are the components of those respective unit vectors. Okay, so this parameterization of the curve represented by the vector value function is smooth on an open interval I when f prime, g prime, and h prime are all continuous on I, and r prime is not equal to 0. Okay? 2 conditions. The first derivatives of each of those scalar functions are continuous on that interval, and the first derivative of the entire thing is not 0 for any value t on the interval. If there is any one little value t which makes it 0, then then it won't necessarily be smooth. Okay? So what does that mean? That leads to example 3. Find the intervals on which the epicycloid c given by this function, okay, and this is two-dimensional, and t is between 0 and 2 pi, is smooth. Find the intervals on which that epicycloid is smooth. So what are we going to have to do? Take a derivative. Sounds like a capital idea. Now, not only do you take a derivative, you're going to be actually taking 3 derivatives. Derivative of the overall function r, because you've got to make sure it's not 0. But in taking the derivative of the things, you're doing the derivative of this and the derivative of that. So you're doing 3 derivatives, basically. These 2 and then the overall. Okay? So taking this one derivative will do all 3 of them. So this will be r prime of t is equal to, oh, wait, I'm on the wrong page. R prime of t is equal to what?
-5 sine t.
-5 times c, t, 5 times sine t, okay, I can't talk.
And then plus 5 sine, plus 5 sine 5t.
Sine 5t, you got it, okay, and that will be your component of your, the I component, the x component of your first derivative, okay?
And then plus 5 cosine t minus 5 cosine 5t.
J, okay? Now, the first thing we have to do is determine, is that equal to 0 anywhere on that interval? Is this, is this and that both equal to 0? Let's see, is that quite right? Are they equal to each other? I won't guarantee it either, is it? Is this equal to 0 at the same place? That is equal to 0 on the interval. See, is r prime of t equal to 0 for any value? Now, one thing they sort of have wrong here a little bit. This should really be the 0 vector, not the number 0. So that should be bolded. They didn't bold it, okay? They didn't say magnitude of it is equal to 0. They said, is it the 0 vector? Okay, now let's see if they got it right in the book. Yeah, they did bold it in the book. They just forgot to bold it here, okay? So, is that equal to 0 and that equal to 0 at the same value t? That's what we have to ask ourselves. And the second question is are these functions continuous? Well, yeah, these are continuous everywhere, right? Sine's continuous everywhere, sine 5t is continuous everywhere, cosine is cosine. Yeah, the derivative functions of f and g are continuous everywhere on that interval. They're continuous everywhere, but on that interval for sure. So the only question we have is, are they both equal to 0 at the same place? Well, let's see. This says that if that were equal to 0, that means 5 sine t is equal to 5 sine of 5t. Okay? Well, you can divide out the 5s, right? I took the minus and moved it to the other side. Okay? So, is that true anywhere? Well, it's certainly true when t is equal to 0. Right? And they're both equal to 0. Okay? Now, the next place where this one's equal to 0 at pi, right? This one's equal to 0 at pi. Well, this is equal to 0 at pi because sine of n pi is 0, okay? So sure enough, so sine of pi and at 2 pi. Okay, those are all 0 at that. So that would be a 0 x component there. Well, let's do the same thing over here. 5 cosine t is equal to 5 cosine 5t, right? Divide out the 5s, that'll be fine. Now, where is cosine t equal to 0 in that interval? Pi halves. Now, is that one, but you see pi halves isn't over here. So it doesn't matter whether that one was or not. Can't possibly, well, wait. Yeah. Okay. And this would be 5 halves pi, and at every half pi cosine t. So that would be, and then at 3 halves pi is the next place, and where that's true, that would be 15 halves pi for that one. Well, yeah, it's 0 there too, but these are not the same values. So the t's here are not equal to each other. So therefore, we don't have to worry about it. These, for the intervals on which the epicycloid given is smooth, everywhere in that interval. In fact, I'd say everywhere for all time and space. Okay, it's smooth because the first derivatives are continuous everywhere, and the first derivatives aren't equal to each other, both equal to 0 and each other at the same value anywhere. Okay? C is smooth. Oh, wait. Sorry about that. Remember, these are independent of each other. So I sort of biced that up some. This will be true anywhere except, there's actually a lot of these. When the x value is 0 and the y value is I don't quite see how they got this. Okay. So they're saying at the point where they're using all these. They say on 0 to pi halves, certainly, but you see they, r prime is not equal to 0. Oh, no. they're saying these are the intervals. 0 to pi halves to pi, pi to 3 halves pi, and 3 halves pi to 2 pi. It's saying those are the intervals on which this is continuous. Okay? For sure, I agree, they are continuous there. But when t is equal to 0, this, admittedly, is 0i, but that would be, oh, okay, I kind of messed this up a little bit. Cosine t is equal to 5t, but it doesn't mean they both are 0 there. I'm sorry, I botched that up. Where it's equal to 5t, they're equal to 5t at these two places. And this is equal, sine t is equal to sine 5t at these three places. So, you see it at t is equal to 0, this would be 5, and this would be 5. So they're equal to each other there. Yeah, so that is right. At pi halves, these are equal to each other, but when t is equal to pi halves, sine of pi halves is the same as sine of 25 halves, okay, because they're exactly 2 pi apart. So yeah, they're right. All these are places where those are equal to each other. So yeah, those are the intervals on which they are. Not at pi halves, because at pi halves, they are both 0 there at the same time. Okay, I was setting where they were both equal to 0 themselves. The whole value is 0, but this is saying where the difference is 0, and that's what we just determined. So, yeah. Okay. And sure enough, let's show how they do it, which is very similar to what we did, I think. The derivative of r is that. Derivative of, yeah, okay. And then the interval 0 to pi, the only values of t for which r prime of t is 0, 0, or t is equal to 0, pi halves pi, 3 halves pi, and 2 pi. Okay. All right. And on the interval, you can conclude that C is smooth on those intervals. And here's what it looks like. And it's certainly not smooth there. From 0 to pi halves it's smooth, from pi halves to 3 halves to pi it's smooth, from pi to 3 halves pi, and from 3 halves pi to 2 pi it's smooth. So sure enough, that's called an epicycloid. Not smooth at the point where it intersects the axis. That the half pies and whole pies. All right. Now these are also sometimes called nodes. In this figure, note that the curve is not smooth at points in which the curve makes abrupt changes in directions. Such points are called cusps or nodes. I'm more used to cusps, but nodes are fine too. Okay? Now, here are some of the properties of your vector value function derivatives of the vector value function. Let R and U be differentiable vector value functions of t. Let W be a differentiable real value function of t. And by the way, scalar function of t, real value. let C be a scalar. So W is a function, it's a scalar function, but C is just a scalar number. Okay. So here are the properties of the derivative of that. This is almost enough to drive me crazy. Do y'all see that, or is it just okay? Good. I hope it wasn't me. Derivative of a constant multiplied by a vector is the constant times the root of the vector, just like it was in everything else. Okay. Derivative of the sum or difference of two vector functions is the sum or the difference of their derivatives, of their derivatives of those vector functions. The derivative of the product of a scalar function times a vector function, strange but true, is the scalar function times the derivative of the vector function plus the derivative of the scalar function times the vector function. So this is if one function is a scalar function, one is a vector function, the product rule goes just like it did before. And the dot product of two, derivative of the dot product of two vector functions would be, again, kind of like you would expect product rule to give you. This is scalar times vector just multiplied together. This is vector times vector dotted together is first times the root of the second, dotted with the derivative of the second, plus the second times the derivative of the first, dotted with the derivative of the first. Because remember, it doesn't matter which order you dot the product. Now, when it comes to vector products, Daniel's here. Okay. Now, I guess a little bit of a review of something we talked about before. Remember, this class does not meet on Wednesday because we're required to go down to Montgomery to waste a day. To go to a meeting. Okay. And therefore, at the end of the class, I'll be giving you the assignment that you do at home for Wednesday. Okay. It's basically doing the YouTube videos that correspond to what we would have been doing on Wednesday, the ones I did the last time I taught the course. Okay, so you watch those and do. Okay, now, cross products, you have to be a little more careful how you do these. Okay, remember I said this one didn't matter which order you did. It does matter down here, so you have to do it this way. R cross U prime plus R prime cross U. This one you can't say the second times derivative of the first cross the derivative of the first. You can't do that. You have to keep them in that order. Now the plus sign, you can put this here and that there. That doesn't matter. But the order of the cross products do matter. Order of dot products do not. Okay? And the order of these do not either. Sixth, the derivative of a composite of a vector function with a scalar function, okay, is chain rule. Derivative of the dot product, the vector function evaluated at the scalar function, then multiply that by the derivative of the scalar function. Okay. Notice here the vector function is always the outer function. Okay. And then, here's the last, and we've hit this several times. If R of t is some constant c, which of course it will be, then R of d dot R prime of t is equal to 0. All right. Now that's a weird way of saying this, because R of t dot R of t is always going to be a number c, a scalar c, except if R of t was the 0 vector. Now, and I guess it still would be true then. So I don't know why they even say it, because I can't think of any circumstance where that wouldn't be a constant, because it's a dot product. So if R of t dot R of t, even if both of them are 0 vectors, that would be the constant 0. Then, well, I guess then you can say, well, maybe the derivative of a zero vector isn't defined? I don't know. I would think it would be the zero vector also. And if it was, then that would still be 0. So I can't think of any circumstance with which that number 7 would not be true. Okay? They just proved property 4. They said proofs of the other properties are left as exercises. So I'll let you mess with that. So let's move on to example 4. Here it is. For R of t is equal to 1 over ti minus j plus log tk, and u of t, second vector function, is t squared I, this flashing light is driving my head crazy, is t squared I minus 2tj plus k. Find each derivative. Okay? So let's find this derivative first. Now, frankly, folks, you can use the rules that we just did, which is for a dot product of two vector functions. What you have to do then, that's this one right here, number 4. Then you do a derivative times and a dot product, and another derivative of a dot product. And frankly, if you just did the dot product of these two vectors, you get a scalar function, take its derivative, it should give you the same thing. To me, this looks like the shortest way to go. Not this way, this way. So let's see. What would we have? What is the, this is d by dt of, let's do the dot product of those two functions. What would that give you? 1 over t times t squared. One over t times t squared. Fairly easy. 1 over t times t squared.
T squared over t.
T squared over t, which is?
1 squared.
It just hit t squared over t. This is t, right? Right? That'd be t. All right. And then these two, a minus 1 times a minus 2t would be
Plus 2t.
plus 2t. And then the third ones would be
Plus log t.
log t. Log t. Because that's times 1, right? Okay? So, this would be d by dt, I like saying that, of 3t plus log t. And what would that be? Anybody?
Three.
3 plus, let's do it with log t.
1 over t.
1 over t. Perfect. Okay. That had better be what the answer is. If it's not, I have some big problems with it. Now, they did it the other way and came out with the same answer, but to me, it was a lot more work. Okay? Now, how about this one? Again, it seems like to me it's easier to do the cross product first and then take the derivative rather than the other way, which is taking the fiddling with all the two cross products. But you have to do a derivative first on this one because they're both u of t's. So let me erase my scratch work here because that is in the way a little bit. And the first thing we got to do is do u prime of t, right? So what's u prime of t? Anybody? 2t I, remember this is a vector. Next.
Minus 2j.
Minus 2j. And aren't you through? Because derivative of 1 is 0. Okay, got it. Okay, now we need to do the cross product of those two vectors. So we're just doing the cross product here. Now remember how we do the cross product? I, j, k, and I repeat I and j. Okay? And then you put down the first one that's listed, which is u. That would be t squared. You tell me the rest.
T squared and 1 over t.
Is no minus 2t.
Minus 2.
You're just doing the u vector, the components of it. Next one. 1. And then repeat your I and j. T squared minus 2t. Okay? Now do the three components of u prime. And that would be 2t
Minus 2j.
minus 2. Yeah,
2j.
right. And then
And
0. And then repeat the first two. 2t minus 2. Okay? Now we do our down diagonals. The first one gives us nothing. Okay? The second one gives us 2tj. The third one gives us minus 2t squared k. Okay, now we'll do our up diagonals. What does that give you?
It'll be 4tk.
4t squared, and that's a positive 4t squared k. Next up diagonal gives us
It'll be 2i.
2i. Okay, and the last one gives you what?
0.
0. Okay, so what we have as our answer is this: 2i plus 2tj plus 2t squared k. Okay? Frankly, I'd want to pull a 2 out of that, wouldn't you? So then we're taking the derivative of d by dt, okay, of, I'm going to pull the 2 out, of I plus 2tj plus 2t squared k. And what would that be? Oh, wait. Sorry. I pulled the t out and I put it back in 2 places. Shame on me. Okay. So that equals 2 times, and when you take a derivative of that, what do you get?
You still assume I, right?
Second?
Just do 1i.
Okay, but you're taking the derivative of 1, which is
Oh, 0.
0. Okay, so 0I
plus 1J.
J.
And then plus 2TK.
Got it. Okay. So there is your derivative of the cross product of those two vectors. Okay. Let's make sure we got the same thing the book did. Oh, and they multiply through. They don't pull out the 2. I was going to say, how did they get that? 2J plus 4TK. Okay. I would have left it out, but yeah, that's exactly what they got. Let's see. Yeah, we already checked the first one. Now, they did it using these rules here. They did the dot product using this, which meant you had to take a derivative of U and a derivative of R separately, and then dot the R dot derivative of U, dot the R prime times U, and then add them together. Whereas what we did one dot product and then took a derivative of the result. Much shorter. Okay? What they did here was take a derivative of U and a derivative of R, dotted R with derivative of U, dotted U, R prime with derivative of U, dotted R with derivative of U, and then dotted the derivative of R with U. Cross, not dotted, cross, and then added those together. That's two cross products, two derivatives, two cross products in addition. What we did was one cross product and a derivative. To me, that's a lot shorter. Okay, but you can do it either way you want to. The good news is they gave you the same answer, which the property said they would. Okay, so that was example 4 on that page. How are we doing on time? We've got another close to 10 minutes, right?
Yes.
Okay, so let's move on to let's see how they did it. I'm sorry, I forgot. This is one that they do show, so I'll erase this. So what they did, I didn't need to erase it. It was on a new page. They took the derivative of the first one, which wound up with a minus 1 over t squared, I, plus 1 over t k. And then they did the u prime, which was that. And then they dotted those together, and they got oh man. That looks so much simpler, doesn't it? Yeah, right. Okay. Now they've got 2 more dot products to do, and this gives us 2 plus 2 plus 0 plus or minus here 1 minus 2 plus 0. It's not hard things to do, but you get them anyway. Okay? Whoops, there's a 1 over t somewhere there. Oh, yeah. No? Oh, I'm sorry, I messed up. Because there was no j on here. So this is minus 1, and then you jump to these. That's 1 over t. And then when you do those together, you get 3 plus 1 over t. I think ours was a lot shorter. Okay? The B part, they did the derivative of u first, and the second derivative of u second. Why in the world did they do that? I'm lost. Oh, I'm on the wrong page. No wonder I'm lost. Oh, yeah, we did it. Oh, yeah, I see. Yeah. We didn't have to take a second derivative at all, the way we did it, okay? And I was thinking, why? Because it was u crossed u prime, taking the derivative of that, so they did need the derivative of u, prime. Of course, they needed U prime. You needed that in the beginning, but they needed U double prime because that was the second. So, a lot of work to do here. Now, this one may actually save a little bit, and here's why. This one, when you cross the vector with itself, you get a 0. Okay? No, I'm sorry. Oh. When you have that one, which is the U double prime is 2I, then that cross right there is 0 because you see this will be a 0, that would have been a, no, that one would have been a 2, and the next one would have been a 0, and then when you go up this way, I'm not really sure. Oh, no, I'm sorry. I said it right. This gives you a vector. This gives you 0. When you cross a vector with itself, because when you cross two vectors parallel to each other, any two vectors, and of course itself is parallel to each other, that's going to give you a 0. Okay? When you dot two vectors perpendicular, that gives you a 0. Cross two vectors parallel. And so that one's going to be a 0. So you already know that's a 0. And then so you just have this one. So this one may be a little shorter this way. And that gives you, it's still several steps, but 2J plus 4TK, which is exactly what we got. All right, good deal.
I liked our way better than that.
What's that?
I was just saying, I liked our way.
Yeah. And by the way, listen to the YouTube today to get what to do for Wednesday.
Yes.
Okay. All right.
You don't know that.
All righty. That's right. It will be Monday, won't it? Okay. I had already turned the page when I forgot to do this one. We've still got a little over 5 minutes, right? Or right around 5 minutes. Right? Okay. So let's look at integration of vector value functions. Guess what? Taking the derivative of a vector value function, you take a derivative component by component. Guess what? Integrating a vector value function, you integrate component by component. Following definition is the consequence of the definition of derivative of vector value function. Derivative definition of integration of vector value functions. If R of t is equal to f of ti plus g of tj, where f and g are continuous functions on a to b, okay, then the indefinite integral or antiderivative of r would be the antiderivative of f of ti plus the antiderivative of g of tj. You just integrate by components. And that's for a plane. And the definite integral, you just put the a to b down here, and then you integrate this one, definite integral of f of t a to b, and g of t a to b, that would be I component and j component, component by component. If you're doing spatially, then you integrate component by component by component. If it's indefinite by definite, then you integrate definitely component by component by component. Just, I hope, like you would expect it to be. You just integrate by components. Okay? Now, the antiderivative of a vector value function is a family of vector value functions. Remember this? All differing by a constant vector c. Now, that constant is now a vector, not just a number c, a vector c. For instance, if R of t is a three-dimensional vector value function, then for the indefinite vector indefinite integral of R of t dt, you obtain three constants of integration. One for the f, one for the g, and one for the h. Okay? Now, because this is by I, this is by I, that's by j, that's by k, those are the components of k, so this will be a vector valued function with f of g, capital F of g, I, g of t, j, h of g, k, plus some vector c1i, c plus c2j plus c3k. So you just get difference by a constant vector c. But it is a vector with various components. These three scalar constants produce one vector constant of integration. Okay? You group your t's together, that's your r of t, since they call it capital, okay? And then this is some constant vector with no t dependence. And this r prime of t is equal to that r of t, okay? So you do your variable components together to get your vector component of the integral, and then do the scalar components together to give you the scalar, constant scalar. So let's do this one. All right, shouldn't be too hard. Do we have time or not? How much? 3. I don't know. We may not be able to. So we'll start this next time. It'll be next Monday. No. Well, you'll see this on the thing. This is where we ended today, but hopefully you'll be able to pick this up. So let me show you where to begin next time. So we got into 12.2, okay? So what I'm going to do is get out of this, and I'll discard this, and I'll get out of this, and let's go to Blackboard. I found this a little easier to do. Well, I did my first class last Wednesday with this, and I went to YouTube, and it looks different on YouTube, so I'm doing it this way here, because this is how y'all would see it. Hopefully, if it'll come up here. Why is it not doing anything? Okay, it's having trouble opening Blackboard. Sorry. I'm sorry. Waiting for Blackboard. Okay, there it came. All right, let's expand this. Now, I've got a lot more courses on Blackboard than you do, so don't worry about mine. If I can get it to come up, my word, this is slow. Here we go. All right, so we need 227. Okay. Spring 1819. Okay, and you go down here, hopefully y'all are familiar with this, you go to handouts, PPTs, and more, PowerPoints, and more. All right, and then you scroll down till you get to the YouTube videos, and there they are. Click on those, and the top one is 14.3 to 15.1. My word. Oh, wait. Okay. You have to scroll down to find 12.2. Okay, so don't go to the top here. Scroll down till you get to 12.2. Ha! There we go. 12.2 to 3. Okay? That's where you'll begin. Okay? 12.2 to 3. And if you do that one, we'll pick up where that leaves off in next time. So this is the one you do for Wednesday. Okay, 12.2 to 3. That one that's in blue right there. You understand? Okay. And then we'll pick up with 12.3 next time. Because we've got, you see, not much more to do in 12.2. I bet you we would have finished 12.3 next time. So let's us begin with 12.4. We'll begin with this one next time. When we come back, we'll begin at 12.4. Okay? I think you can follow everything else there. Okay? Good deal. All right, so I'm going to get out of this then. So you do 12. So actually, you're going to do 2. You're going to do 12.2 to 3 and 12.3. You'll do both of these here, and we'll begin in 12.4 next time. All right? Okay. and I'll get out of here. Okay. And let me load this.